Hello friends, welcome to YouTube channel Electronics for You. Friends, in this video I will solve some examples of steady state error and static error coefficient. So before this video I had already solved two examples of on this same topic. So this is the second part. You can watch this video over here, and if you have already seen this video, let us solve some examples here. It is example number 3. The control system is having unity feedback, has g of s equals to this term, okay, 100 over s times 1 plus 4s times 5 plus s. Determine static error coefficient and steady state error if input is r of t equals to 2 plus 4t plus t square by 2. So this is the given input over there, but g of s is given as this one, and unity feedback, it means that h of s equals to 1. H of s equals to 1 and g of s is this one, and therefore the multiplication of g of s and h of s is equal to this term again. Okay, we will use this term for finding the static error coefficient, that is generally called as error constant or static error constants also. So we are having three different static error coefficients, that is positional error constant, velocity error constant and acceleration error constant, represented by Kp, Kv and Ka respectively. The formula for Kp is limit s tends to 0 g of s into h of s. Kv is equals to limit s tends to 0 s into g of s into h of s. S is added over here, and for Ka, that is acceleration error constant, it is s square, and the respective steady state error we will use this formula. Now to calculate static error constant we will use this formula. We have already seen this, and now I will put g of s into h of s equals to this term here, and therefore we will get equation like this. Now let us apply limit here. Now as s tends to 0 is here, we will get 100 over 0 multiplied by 1 multiplied by 5, and therefore it is equals to something divided by 0, that is infinity. Now similarly we will get Kv here, this s and this s will get cancelled, and we will get it as 100 divided by 1 multiplied by 5, it is equals to 20. And Ka, it is now this s and 1s from this s square will get cancelled, and 0 multiplied by anything, let it be 20 in this case, so Ka equals to 0. So in this way we get Kp equals to infinity, Kv equal to 20 and Ka equal to 0. These are our static error constant. Next we have to calculate the steady state error, and in this case the given input is this one. Now let us apply the Laplace transform here, and we'll get it as r of s equal to, we replace this r by capital R, and of t is replaced by s while applying the Laplace transform. For 2 we are having Laplace transform as 2 upon s. For 4t the Laplace transform 4 will remain as it is, and for t Laplace transform is 1 upon s square, that is we will get 4 upon s square here, and last term, that is for t square we get 2 into 1 upon s cube. Okay, so 2 upon s cube we can write it here, and already 2 is there in the denominator, so this 2 and this 2 will get cancelled, and therefore we will get r of s equals to 2 by s plus 4 by s square plus 1 upon s cube. Now look at this equation. This is very special equation. Here it is 2 upon s plus 4 upon s square plus 1 upon s cube. Now a upon s is the equation for A upon S is the equation for step signal. A upon S square is the equation for ramp signal, and A upon S cube is the equation for a parabolic signal. It means that the same input signal is consisting of all these three standard taste signal, and therefore we can write here, let us write the magnitude. Okay, A is equals to 2. Now I will indicate here A1 equal to 2 here. Now A2 is equals to 4 and A3 equal to 1 here. I'm just writing here, and therefore steady state error is the addition of all these three types of input. So it's the sum of all these three types of input. Therefore ESS equals to A upon, for step signal it is 1 plus Kp. For ramp signal it is A upon Kv, and for parabolic signal it is A upon Ka, and respective magnitude is indicated by A1, A2 and A3 respectively here, and therefore putting the values, A1 is 2 and 1 plus Kp. Now see here that we got a value for Kp as infinity. Sorry, Kp as infinity. Now Kv, we got a value for Kv was as 20, so it is 4 upon 20, and for parabolic it is A3 is equals to 1 and Ka equal to 0. Now after solving this 2 upon infinity will be here, 1 plus infinity means infinity, so 2 upon infinity is equal to 0, plus 4 upon 20 will be there, and plus 1 upon 0 will be infinity again. Now something is added with infinity means we get ESS equal to infinity. Here our steady state error will be infinite. It means that we are having an unstable system here. In this case, if we apply this input, so in this way we calculated our static error constant and steady state error. Let us solve another problem. Now unity feedback system is given, G of S is given as this one, and again we have to determine these type of system, static error constant and steady state error if input is this term. Okay, now let us solve this problem. G of S is given this one, and H of S is actually, it is unity feedback system, therefore H of S equals to 1. Now multiplication of this, that is G of S into H of S, will be equals to 100 times S plus 1 over S square times S plus 2 times S plus 10. Okay, so this is our equation, and we have to find the type of system, and type of system are the number of poles at origin for an open loop transfer function. This is open loop transfer function, and number of poles means the power of S. Here the power of S is 2. It means that it is a type 2 system, as 2 poles are at origin, and hence it is type 2 system. Now let us find the static error coefficient. The formula for this is this one, that is Kp is equals to limit S tends to 0 G of S into H of S. For Kv, here S will be added and here S square will be added for Ka. Now just put the value of G of S into H of S. We have already calculated it, and after calculation, after putting this value, we will get equations like this. Okay, now let's apply the limit again. In this case, we will get it as, this is 100 divided by, the value of S is 0, to 100 divided by 0. Okay, so it's nothing but infinity. For Kv, again if this S and one of this S square, one of S from this S square is get cancelled, again it will be 100 divided by 0. So infinite again, and Ka. Now this square and this square will get cancelled, and it is 100 multiplied by, put s equals to 0, it is 1, and here it is 2 multiplied by 10. So we will get Ka as here 20, that is 5. Ka equals to 5 in this case. So we got all static error constant, that is Kp equals to infinity, Kv equals to infinity, and Ka equals to 5. Now next is to find the steady state error, and to find steady state error our given is R of t. So we will use same technique again, taking Laplace transform here. We will get R of s equal to for 10 we will get it is 10 by s. For t, so it is 4 divided by s square. The Laplace transform of 4t is 4 upon s square, and for t square we will get it as 2 multiplied by 2 upon s cube for t square, and 2 is already given there, so this 2 and 2 will get cancelled, and we will get R of s equal to 10 upon s plus 4 upon s square plus 1 upon s cube. And therefore again same things are here, it's a combination of step signal, ramp signal, and parabolic signals. Therefore let it be a1 equals to 10, a2 equal to 4, and a3 equal to 1. So we got a1 equals to 10, a2 equals to 4, and a3 equals to 1 in this case. And therefore putting values now, putting these values in formula, ESS will be the combination of addition of all these three, that is a1 over 1 plus Kp for step signal. For ramp signal it is a divided by, that is a2 divided by Kv, and for parabolic signal it is a3 divided by Ka. Now just put the values here. a1 is equals to 10 divided by 1 plus infinity, because Kp is infinity. a2 is 4 over infinity again, and it's 1, that is a3 upon Ka. The value of Ka was what we have calculated, 5. So just put the value as 5 here. Now it is 10 upon infinity. 10 upon infinity is 0. 4 upon infinity is again 0, and 1 upon 5 is 0.2. So in this way ESS equal to 0.2. So this was our problem, second problem. In this we got ESS equals to 0.2 as our final answer. So in this way we can solve this example. Some more examples will be solved in next video, where we will find the value of K to stabilize the system, and some videos of Hindis are also available, because I am making videos for control system in Hindi as well as in English. And in Hindi and in English playlist I generally solve different problems. So if you know Hindi, you can refer these videos also for your practice. Thank you.